So last class, actually, what we have seen is at the end, we have taken a small problem and designed the algorithm for the problem. Then also we have discussed how to prove the correctness mathematically. Then how to do the analysis in terms of time and space, right? So this is what we have discussed. Okay, now let us see. Okay, in the algorithm design, three parts actually we mentioned. One is design. One is design. Other one is correctness, and third one is analysis. So, with respect to that problem of finding the maximum value available in the array, we have discussed these things. Now, let us see a little more details in these concepts. So, that's what this class deals with. So, as far as the design, first let us take design. As far as the design is concerned, there are several design techniques are available. Anyway, the problem which we have taken is a very small problem. Therefore, straight away we can write the algorithm. Okay, so the design part is not complicated. However, if you take some problems, that may be not so simple. And based on the property of the problem, we have to choose appropriate design technique. And basically, the aim of this course or objective of the course is to design various, to study various design methods. Okay, and we are not going to see all the design methods, but some of the very standard and very important design techniques that we discuss in this course. There are several design techniques available. One is called divide and conquer. Maybe in case a problem that can be divided into small sub-problems, then we can go for that. Okay, so that's why I said, based on the problem properties, we have to choose that. And other design technique, greedy algorithm there, dynamic programming there, branch and bound there, backtracking there. For example, if you take dynamic program, the problem should be of optimization in the nature. Something like maximization or minimization. Okay, even greedy also like that. Okay, so there are several design techniques available. The first task is to find out which design method that can be used. Okay, so anyway, now it is too early to see that. Anyway, we are going to see some of the design techniques at the later moment. So we can see that. Okay, now I can stop explaining further on this concept. So next one is called the correctness. So as far as the correctness is concerned, what we stated earlier is we have to mathematically prove the correctness of the algorithm that we have designed. So there are several proof techniques available, because sometimes what happens, if you are not, using the proof properly, so that's why the mathematical proof, this is once this proof is correct, everything will be correct. Sometimes if you are not applying the concept properly, okay, or if you make small mistakes without knowing the concept, then the whole proof that goes off. So one example I can say that, for example, let us take B is equal to A. Okay, we assume that A and B are the two variables and both having the same value. So B is equal to A. Now, in this, I am multiplying A both sides. Multiplying A both sides. So what happened? This becomes AB and the right hand side becomes A square. Correct, no? Okay. So if you multiply A both sides, what we get is AB equal to A square. Now I subtract B square both the sides. So left hand side becomes AB minus B square and right hand side becomes A square minus B square. Okay. Now what happens? The left hand side B is common, so that B can be taken out, and the remaining thing is A minus B. Okay, remaining thing is A minus B. And the right hand side A square minus B square, so its value is A plus B into A minus B. So we can write A square minus B square as A plus B into A minus B. Now both sides that is having A minus B common, so I can cancel it. So remaining thing is B here, and here A plus B is there. Actually A is equal to B. That is what our assumption. So A is equal to B. So I can replace A with B. So this becomes 2B. So now B is common. If I cancel it, what happens? This is 1 is equal to 2. So is it correct? So we proved that 1 is equal to 2, right? Is it correct? So where is the mistake? So as far as the derivation is concerned, everything is going fine. Okay, I haven't applied anything, which is unusual. Normal algebraic, evaluation only I have done, right? But there is a mistake. What is a mistake?
Sir, we cannot cancel A minus B, sir.
Yeah, why?
Because A is equal to B, A minus B will be 0, sir. We can't
0,
cancel.
exactly. Very good, very good. Okay, so actually we are cancelling means we are dividing it by 0, right? So both sides we are dividing it by A minus B, but A minus B is equal to 0. So we are dividing it by 0. If some quantity is divided by 0, it's undefined, okay? So that's what the mistake we have done. So we cannot cancel it. Okay. So when you are applying mathematical proof, you have to be very careful. So sometimes if you make a small error in it, then the whole proof will be wrong. Okay. So that way, if you prove the correctness, it will not be useful. Okay. And as I mentioned, there are several proof techniques available, nearly 45 proof techniques available, but not all are important for us. But most of the algorithm which we study in our course that falls into one or two proof techniques. So let me explain what the proof technique, how it is to be dealt with, so that later on that will be useful. The first one is called mathematical induction. Mathematical induction. I hope all of you might have studied mathematical induction. Have you studied or not?
So we have
Anybody?
studied, sir.
Pardon?
We have studied it in the second semester.
Second, you studied in the second semester. Okay, very good. How mathematical induction works? Can anyone explain how mathematical induction works? Actually, there are two principles of mathematical induction. Have you discussed? Studied that? So there are two principles. One is called first principle of mathematical induction, and other one is called second principle. Sometimes the first principle of mathematical induction is called the weak principle of mathematical induction. And the second principle of mathematical induction, that is called the strong principle of mathematical induction. Okay, we can come to that a little later, but basically, can anyone explain how this mathematical induction works? Actually, how many parts are there in the induction proof? 3 parts, right? 3 parts. How we do that? The base condition, basis. Then it is called hypothesis. Hypothesis, something like assumption, right? We are assuming something. Then based on the hypothesis, we will try to prove that. So there are 3 parts we have to consider in the induction proof. So maybe if you want to prove it, concept, okay, some index variable we have to consider. For example, index variable is n. Then basis is for small value of n, maybe I can say that n is equal to 1. We proved it, okay? And I assume that hypothesis, that is assumption, therein we assume that when the value of n is equal to k, proof hold good. Okay, the statement of the theorem hold good, something like. Then based on the hypothesis, I try to prove it for k plus 1. And I conclude that, if I have done this for all values of n, the statement would be true. How? If I do these three steps, I am telling that the statement given or a theorem given. Okay. So that is hold good for all values of n. How is it? You see, when you take these two steps, what we are actually doing, if the hypothesis, this assumption, right? So if you assume, or if you think the statement is true for n is equal to k, and based on that we prove it for k plus 1. So already we proved it for n is equal to 1. So according to that, 1 plus 1 it is true, because if it is true for k, k plus 1 it is true, right? So already we prove it for n is equal to 1. So 1 plus 1, 2, it is true. So when it is true for 2, what happens? 2 plus 1, 3 also it is hold good. So for all values of n, it will hold good, right? So this is what the fundamental idea behind the mathematical induction. And what we discussed here is called the first principle of mathematical induction, or sometimes it is called the weak principle of mathematical induction. So why we want the two principle is because certain problems can be solved using first principle and certain problems can be solved only using second principle or strong principle. So that's why we having two. We take small examples and illustrate so that you get very strong idea. About it. Okay, first let me take one problem and try to prove it using mathematical induction. The problem which I take is 1 plus 2 plus etc. plus n is equal to n into n plus 1 divided by 2. So this is the formula, right? So this we have to prove it, that this formula is correct. Okay, mathematically we should not take some example and tell that okay it is coming right. So that's not a proof. For counter examples, you can take one particular instance and you can always say that it is not hold good. For counter example, it is okay, but whenever you are trying to prove that, you cannot take like that. You cannot take examples and prove that. You have to take, a variable, okay, so that it will hold good for everything. So mathematical induction we are taking. So first, if you take basis condition, so basis we can start with a small value. So n is equal to 1 we are taking. So in this formula, if you substitute n is equal to 1, on the left hand side, what happens? 1 plus 2 plus up to n is equal to 1 means only one value will be there, 1. Okay, start with 1, right? And the right hand side, when n is equal to 1, it is 1 into 2 by 2, right? So 2 cancel. So that implies 1 is equal to 1. So proved, right? So proved for the basis condition. Proved for the basis. Proved for the basis. Now the hypothesis, assumption. We assume that it is hold good for k, some k. Okay, this is only assumption. Okay, so based on the assumption only, we have to prove it, because, and one more thing is, whenever we are trying to prove it for k plus 1, we have to use this assumption, then only the statement is correct. If you are not using this assumption, then we cannot conclude. Okay, so that's very important. So if you assume that it is hold good for k, then what the statement is? 1 plus 2 plus etc. plus k is equal to, what is the right hand side? K into k plus 1 divided by 2. Now with this, we have to go for the proof, that is for n is equal to k plus 1. So if it is k plus 1, then the left hand side will be, okay, 1 plus 2 plus etc. plus k plus then k plus 1. Okay, one more term is added. But already we know the value of this based on the hypothesis, right? So that's why I said whenever we are trying to prove something here, some place you have to make use of whatever you assumed or whatever the hypothesis you have taken. So if you are not taking, then the proof is not correct. Fine. Okay. So what we can do? We can substitute this value here, right? So this implies. So what's the value for this term? That is k into k plus 1 divided by 2, and here it is k plus 1. Sorry, k plus 1. Now we can take LCM. So if you take LCM, LCM is 2, and here k into k plus 1, and here it is 2 into k plus 1, right? So in the numerator, k plus 1 is common. Numerator k plus 1 is common, so that can be taken out. And if you take k plus 1, here k and here 2 is there by 2. Okay, now we have proved, because now our value of n is equal to k plus 1. So n into n plus 1 divided by 2. So we got, hence we proved it. Okay, and as for the explanation I have given, anyway, by assuming this we have proved it. So already we proved it for the base condition. So for all values of n, this hold holds. Okay, this is the induction. Now, this is the first principle of induction. Now let us see when the second principle of mathematical induction to be used. There are, as I mentioned earlier, there are certain problems which will be solved only using second principle, but not using the first principle. Let me take one example. Therein, we can go for a strong principle of mathematical induction. So all of you are aware that if you take any integer, maybe let us say n is an integer. Any integer can be described as the product of prime numbers. Am I correct? Any integer can be described as product of prime numbers. Is it true or not? Is it true or not?
Yes, sir.
Yes. That we have to prove. That we have to prove now. Okay. So before that, let us see what the strong principle of mathematical induction. The strong principle of mathematical induction that says that once again three part. One is the basis. Therein we take for a small instance n is equal to 1 or 2 like that. Then we take the hypothesis. The difference is only in the hypothesis. In the weak principle, we assume that n is equal to k, but here we assume that n is less than k. So that is, here strong principle is we assume that for all values less than k, it holds. Then we try to prove it for n is equal to k. Then the next value. Once again, the logically is same. For example, if you start with n is equal to 1, anyway, for all values less than k, it's hold good means, okay, including k minus 1, including k minus 1. Therefore, anyway, even if you start from the basis 1, then 1 plus 1, 2, okay, then 1 and 2 it is hold good, then for 3, then 1, 2, 3 it is hold good, for 4 like that. Once again, it satisfies for all values are there. Okay, now we can come to a problem. This is what second principle or a strong principle. This principle we are trying to use that. If you take an integer n, if n itself is a prime number, then we solve the problem automatically, because if n is a prime number, that's a product of prime number. Nothing else to prove it. It's trivial, isn't it? Okay. Suppose n is not a prime, then only the question is coming. It's a composite number. If n is not a prime, then what you can do? It can be a multiple of two integer values, n1 and n2. It can be a product of two other integers. n1 is an integer and n2 is an integer. But this n1 and n2 are strictly less than this n, because n is not a prime number, right? N is not a prime number. So if n is not a prime number, n can be written as a product of two smaller integers, that is n1 and n2. Now, as far as the strong principle of hypothesis, what we stated, for all values of n which is strictly less than that, it's hold good. So anyway, we have to prove it for n. So n1 is less than n and n2 is less than n. So based on the hypothesis, we know that N1 is the product of N1 can be written as a product of prime numbers. Okay, maybe you can say P1, P2, etc. And N2 can be written as a product numbers, prime numbers, that is Q1, Q2, etc. So now if you multiply these two, this is also a product of prime numbers. So any integer, if you take that, that can be represented as a product of prime numbers. Product of prime numbers. So now you see here, if you apply first principle, is it possible? It's not possible, because the value of n1 and n2 is not just n minus 1. It is some value which is less than n. It may be 2 or 3 or 5 or something like that. We do not know. It may be some, it is strictly less than that, and it is not just n minus 1. And hence, in this case, only the second principle hold good, but first principle we cannot apply. Okay, so we have two things in the mathematics: first principle and second, or weak principle and strong principle. Okay, so depending on the nature of the problem, we have to make this up. Then the second proof technique, that is called proof by contradiction. Proof by contradiction. So what is proof by contradiction? So if you want to prove something, you will assume that the statement not hold good. You assume that the statement not hold good. Then from that assumption what we have made, you do something. Okay, so conceptually whatever you want to do, you do that. Finally, that will lead to a contradiction to the known fact. Okay, or contradiction to something what we assumed. So in that case, what we'll say that is, we will say that our assumption is wrong and against the theorem is proved. So this is called the proof by contradiction. Once again, I can take a small example and illustrate. The statement which I am taking is, I want to prove that there are infinitely many primes. Many primes. So primes mean prime numbers. There are infinitely many primes. That means there are infinite number of primes are available. Infinite number of primes are available. So this we have to prove that. We have to prove that there are infinitely many number of prime numbers are available. Okay, so here we are trying to prove it using a proof by contradiction technique. So in the proof by contradiction, as I mentioned earlier, what we assume is, we assume that a statement which is contradictory to this one. So here we say that infinitely many primes. So we have to assume that there are only finite primes. Okay, we assume that. Assume there are only finite number of primes. There are only finite number of primes. So this just contradict to that particular statement, that which we want to prove. We have to take the assumption. So if there are only finite number of primes, we can list out because only finite number. Okay. So without loss of generality. Okay. Mathematically, most of the places we might have used without loss of generality. What it means? Without loss of generality. As teacher said, you also used, right? Without loss of generality. So without loss of generality in the sense that if you take like that, the statement is not going to be affected. The proof is not going to be affected. So whenever such places we take something, we have to mention that without loss of generality. So by taking that, anyway, the proof is not going to be affected. Whether you can take this way or that way, it does not matter. Okay. So here, without loss of generality, we assume that the finite number of primes are P1, P2, etc. Pn. We assume that only n primes. N is a finite number. This n may be anything, I don't know. So if I assume that there are n primes, that primes will be P1, P2, etc. Pn. So I have listed out all the prime numbers. I know. because my assumption is only finite number of primes, right? Okay. Now, based on these prime numbers, I am trying to form another number. So let the number be Q. Let the number be Q. So how I form this Q is 1 plus the product of these prime numbers, that is P1, P2, etc., Pn. The product of this one. Okay, now Q is a new number. My question is whether Q is a prime or not. Suppose it is not a prime. Okay, suppose this Q is not a prime. Then if you divide that number by a that number should be divisible by any prime number, okay? Because we know that any integer can be written as a product of prime numbers, right? Product of prime numbers. So if you divide by a prime number, the remaining thing should also be a product of prime numbers. Or it should be, or we can say it should be divisible by. It should be divisible by a prime number. But our assumption is we have only n primes. Then primes are P1, P2, etc., Pn. So if I divide it by P1, what happens? I get remainder 1. Because this term goes off and remainder 1. So if remainder 1 comes, it cannot be divisible by P1. So divisible by P1 means remainder will be 0. Okay. So if I divide it by P1, I get a remainder. Similarly, P2 also the same thing. Pn is also the same thing. And all the things, all the primes, because these are the only primes. So if I take any one of the prime and divide, the remainder is equal to 1. So that means this cannot be divisible by any prime number. If it is not divisible by any prime number, this Q itself is a prime number. Q itself is a prime number which is larger than this. It is larger than this because it's a product will be added with a 1. So that is larger than that. So this here we get a contradiction that because our assumption is there are only finite prime numbers and the finite prime numbers are being listed out. Now what happens is we are able to find one more prime which is larger than this. So that means this way we can extend it, this way we can extend it, and there are more number of primes available, and again there is a contradiction to this assumption. There is a contradiction to this assumption, and again we conclude that there are infinitely many primes. There are infinitely many primes. This is called the proof by contradiction. If you have any doubt, you can clarify now. Assume that you got the concept correctly. May I assume that? Understood or not?
Understood, sir.
Okay. Then one more proof technique also commonly used in algorithm. As I mentioned, there are several techniques. I don't assume that only, these are all there. Okay, there are several things available. Because anyway, this is not a mathematical class. This is an algorithm class. We cannot go with all the mathematical concepts. Okay, so that's why we restrict with whatever is really important. The next one is called the direct proof. Direct proof. So based on whatever the axioms given, okay, or whatever the properties given, we straight away prove it. I can give one example of the direct proof, how it looks like. The statement, okay, I can take a problem. Statement is A divides B and B divides C, then A divides C. So this is what the statement. A divides B and B divides C, then we can say that A divides C. Here, how the direct proof? If you say A divides B means B can be written as some constant K1 into A, right? A divides B. Similarly, B divides C means what you can say C is equal to some constant, let us say that is K2 into B. Okay, now if you take this, C equal to K2 into B, B is equal to K1 into A. So that is K2 into K1 into A. So K1 and K2 is, K1 is a constant, K2 is a constant. So K1 into K2 is also a constant. So C equal to some constant multiple of A, that implies A divides C. So based on whatever the properties given or whatever the axioms given, so we straight away apply, and finally we get the answer. So that is what called direct proof. I think these three proof technique would be sufficient for our course of study. Okay. Therefore, out of the three things, design and correctness. Okay, these two we have seen. Now we are going for the analysis. Okay, little more details about analysis. Okay, in the analysis, what we analyze, what are the factors we analyze? One is called the time, and other one is called the space. Okay, one is called the time, and other one is called the space. Whenever we are taking a problem and design the algorithm for the problem, our main objective is the algorithm what we design should take minimal time, okay, minimal time and a minimal space. For example, if you take sorting, okay, maybe you might have written code for some sorting techniques in the C program, I don't know. But sorting everyone knows, it may be in the increasing order, decreasing order. There are several sorting techniques available. Insertion sort, selection sort, merge sort, quick sort, table sort, bucket sort, radix sort, like this, several sorting techniques are available. Obviously, you may get a question. Any of my objective is to start the numbers or maybe the strings either in the increasing order or in the decreasing order. Then why should I have these sorting? There's so many sorting techniques. Okay, so these sorting techniques has not come just like that. So these sorting techniques based on the analysis, first their aim is to sort something. Those they write the algorithm. That algorithm may not be efficient. That means that algorithm takes more time and more space. Maybe either they try to reduce the time or try to reduce the space. Finally, they get a better algorithm and they name the algorithm as something else. Okay. Here, anyway, we are not looking straight away into the time and space, but there is a very fundamental concept that we have to remember while doing the analysis. As I mentioned earlier, whenever we are trying to design an algorithm for a problem, our objective is to reduce both the time and space. But what happens is, when you try to reduce this time and space, these two factors can be reduced only up to certain level. Only up to certain level. After that, when you try to reduce one factor, for example, if you want to reduce the time, the space will automatically increase. Vice versa, in the similar way, if you try to reduce the space, the time will be increased. So remember, whenever we are trying to reduce both the time and space, this reduction is possible only up to certain level. After that, whenever we try to reduce one factor, other factor will automatically increase. And this is what called the trade-off. This is what called the trade-off. And here, this trade-off is between the time and space. When I try to reduce the time, space increases. Okay, whenever I reduce the space, the time increases. So the trade-off is between the time and space. So this is called time-space trade-off. Okay, this is called time-space trade-off. Okay, once again I can take small example and illustrate so that it will be clear for you. Okay, let us take one problem now. We assume that we have an array. Okay, we have an array. Array concept everyone knows, right? Because already you have studied C programming. So therein you might have used arrays, integer arrays, floating point arrays, something like that. So here we assume that there is an array. Array is sequence of values which are been stored in the consecutive locations. Okay, suppose there is an array. This array is having certain values. Okay, we can assume that size of the array is n. So starting with the 1 and ending with the n index. And some values are available. The problem is this one. We have to reverse the array. Suppose these are all the characters. Okay, when you reverse that, the last character will come to the first position, something like that. First character goes to the last position. So reversing the value, okay, reversing the array. So this is a problem we consider. And I am not writing any code, but conceptually I can explain that is more than sufficient in this case, because our aim is to know about what is the time space trade-off. So whenever I want to revise this, what we can do? Suppose this is the array called A. The name of the array, that is A. I have to reverse the array A. Therefore, I can define another array B, okay, of same size, B of same size. So here also n values are available. So 1 to n. Now I can put a for loop. Maybe I can say for I is equal to 1 to n. What I am trying to do is, anyway, I can conceptually explain here. Anyway, here also I can write. No problem. So I read the first value and that value will be placed in the last position. Then second value I read and that will be placed in the last but one position. So whenever I goes, the insert value will be from the last. Okay, if I proceed like that, when I reach this n, that value will be placed in the first position. So if I do that, what happens? After that, if I return B, array B, that will be the answer, because array B is in the reverse order. So that we got, right? So this is what my algorithm. Okay, now let us analyze it. Okay, the time space concept is considered in the analysis side, right? Analysis side. So we can analyze that. Okay. First, the space we can consider. Space is the storage requirement. So this is what we discussed even in the last class, right? Storage requirement. How much storage that is needed? So already we have an array. This is an input array. So input array should have n storage spaces, because there are n values available, or array size is equal to n, right? This is the input array. So that is n space required. So n. Then we are taking another array, that is B, which is output array, which is the output array. Then output array is also same size. So n plus n. So that is equal to 2n. So 2n is the storage space. Maybe you can say this I also. Maybe if you write the code, okay, 2n plus 1, no problem. One more variable. So space requirement is 2n plus 1. Now the time requirement, let us see. Time requirement is we are reading the array A one by one. So there is a for loop for I equal to 1 to n. So the number of iterations this for loop that does is n times, right? So every element we have to read and write it here. First element, then second element, then last element, something like that. So every element we have to read. So for each and every read and write, the statements are available here. Accordingly, that much number of iterations that happens here. And that can also be determined based on the how many times this variable I goes, the ranges. So there are n times. So that means the algorithm will take n unit of time. Okay. So because n iterations, we have to do that. Or what we can consider is here actually what we have is we have a B array that you want to assign only one assignment statement. Okay, A of something. Okay. So only one assignment, 1 unit, and that 1 unit of time will be spent for n iteration, and hence we mentioned that time is equal to n. So space is equal to 2n plus 1 and time is equal to n. Okay, now are we happy with this algorithm? I have a problem. I solve the problem. So this is what we think still now. Maybe even up to plus 2 level, you might have thought like now you should not think because you are a computer scientist. The way in which the others write in the code and the way in which you write in the code should be different, right? So you have to analyze properly and you have to judge that whether this code is okay or not, or further refinement that need to be carried out. So I got an algorithm, I got the output. Okay, if you are feeling that output is sufficient, then it's okay. But if you are a good professional, you should not think that way. If that's the case, my question is whether this algorithm is okay for you or not. How you finalize it? Okay, I think time is up, right? So students, you have to join at the right time because you see already time 5 minutes in the next class 10:30. No, so I can take 5 more minutes and finish up. Otherwise, this concept will be hanging. Okay, so now you see, as far as the time is concerned, yeah, anyway, I can quickly go through that. Time is n, it's okay because I have to reverse n such values, and against my time n is okay for me. But what happens is I am using extra space for reversing n values. I am taking one more n, that is 2n is required. That I am not happy. So here, what the improvement I have to do is I have to reduce the time. So how I reduce the time? I should not use the second array. If I use another array for output, automatically the extra n will come. So I should not use the extra array. Rather, what should I do is I should handle with the first array, the input array. Okay, I have to handle with the input array. How I can do that? So this is our array A. Okay, this is our array A. Now what I do is I swap the first and last element. Swapping. Then swap second and last but one element like that. If n is odd, then finally it will end with one value that therein you need not to do the swapping. Or if the n is even, then last n by 2 swaps that may be required, right? So even if you do that, what happens? The last element comes to the first and first element goes to the last, something like that. And we get the output array. But in this algorithm, there is no extra array and against the space is reduced. So now in this case, what is the space requirement? Can anyone say how much space required?
N plus 1.
N plus
1.
Why 1?
For the iterating variable.
Iterating variable, okay. Apart from that,
You may need a temporary variable for
a temporary variable. You have to do the swapping. Generally, if you want to do your swapping, you have to have a temporary variable, right? Temporary variable. For example, you want to swap a of 1 and a of n. Okay, then temporary variable, you have to put a1. Then you will say a1 is equal to an. Okay, then an is equal to temp, right? Like that. So these three statements that is required for doing the swapping, 2 elements swapping, 3 statements required. So one more variable, maybe you can say that n plus 2. So now you see n plus 2, n may be reduced from 2n plus 1, 2n plus 1 to n plus 2. So there is a reduction in the space that we achieved. Okay, but this constant factor we don't consider. Anyway, when we discuss in the next class, you will be knowing that whether this 2 is considered or this 1 is considered like that. So that discussion we can have it in the next class. So our aim is to reduce the space because this is a bottleneck, something what we are the issue what we assumed here is the space. The space requirement is almost a double. That we have to reduce. So we change the algorithm design strategy. And when you change that, the space is reduced from 2n plus 1 to n plus 2. Okay, it's good. Now let us see the time. So now there are 3 statements. These statements should be put in a for loop, right? For I is equal to 1 to the half of the size, n by 2, we have to do that. Okay. If you go like that, first to last, like that, number of swap required is n by 2. Okay. So there should be a for loop that goes for n by 2 iterations. And each iteration, there are 3 steps. Each iterations, there are 3 steps. So what is the total time? That is 3 steps are required in each iteration and number of iteration is n by 2. So 3n by 2. 3n by 2 is the time. So 3n by 2 time is equal to 1.5n, right? 1.5n. Now what happens when you try to reduce the space? What happens? Time is increased from 1 to 1.5. Okay. So this is what called time shift trade-off. So remember, time and space factors are concerned. We have our objective, overall objective to reduce this, but this reduction is possible only up to certain level. After that, if you try to reduce one factor, other factor will automatically increase, and that is what called a time space trade-off. Okay, this is an example that gives a clear-cut idea of what the time space trade-off. Okay, so we can continue in the next class.